Okay, in this section we're going to take a look at the continuity and behaviors of various graphs. So when we look at these, in the most simplistic terms, what we're determining in continuity, or a graph, is continuous if you can trace it without lifting up your pencil, meaning that there's no breaks or gaps. So when you look at the function here on the left, we see very clearly that if I start from left to right, as I trace this graph, I have to break or stop and lift my pencil to come down here. And then again, I have to mark this point separate here and then continue on. Whereas this graph in blue here on the right just goes on infinitely to the positive direction and the negative direction, and I never have to lift or remove my pencil from the paper. So in the most basic terms, this would be a continuous graph. So continuity as it's defined is that the graph can be traced without lifting your pencil. It's a function is continuous at any number, the number c, if there's a point on the graph with the x-coordinate c and the graph passes through that point without a break. So the point has to exist first off. So when you substitute that value of x in and you crunch the numbers through the equation, you will get an output of y value. So there must be a point c as reference on the graph. And as you approach, when you substitute in that value, you will approach a given value for the function. So there's different types of discontinuity in graphs. First one we're going to talk about is an infinite discontinuity, and you see these all the time with vertical and horizontal asymptotes. And what that means is that the absolute value of the function f of x becomes greater and greater as the graph approaches a given x value. And this would be an example here if we graph that real quick. Put that in as a fraction, or as a rational function, 1 over, say, x squared. We see we actually have this vertical asymptote right here. And we know that's going to occur because when I have a variable in the denominator, anytime that approaches 0, because we cannot divide by 0, we will create that asymptote and it will error. So there is a discontinuity, and that's called infinite discontinuity at that value. There's also jump discontinuity, and you saw it in the graph when we started here, and it indicates that the graph stops at a given value of the domain and then begins again at a different range value for the same value of the domain. If we scroll back up to that graph real quick, we'll see what it's saying is as I begin to trace this right here at this value or this input of x, all of a sudden the graph jumps back down to this section and then continues forward. So that is jump discontinuity. And there's also point discontinuity. Again, that was seen in the graph up above, where there's a value in the domain for which the function's undefined, but the pieces of the graph match up. So again, looking at this graph as a representative, when I get to this point here, I have a break noted by this open circle in the graph for this specific value, and that occurs specifically at this one given point right here. So that is point continuity, or discontinuity rather. In order to test for continuity when given an equation, a couple things we need to check for. To verify that it is continuous at x equals c, or it is continuous at x equals c, if it satisfies the following conditions. It needs to first and foremost be defined at that value. So f of c exists. When I plug in that value of c, I get an output, so it must exist. And then these bottom two are very similarly related. What they basically state is that as I approach the value, so as I get very, very close, and what I'm substituting in here for that value of c, I get very, very, very close to that output f of c. And you'll see what that looks like here. So we're asked to determine whether the following functions are continuous at the given point using the continuity test. If not, state what type of discontinuity there is. So let's see. So again, here's my 3 steps, and what that really boils down to is it looks like this. Okay. Make just a couple of changes here. Erase that. And so the first thing is I want to evaluate this. So again, so f of x is this, negative 2x plus 5, and I'm checking to see if it's continuous at this input, x equals 3. So I go ahead and I just substitute 3 in here. Negative 2 times 3 is negative 6 plus 5. So f of 3 equals negative 1. So that checks off the first one. This point does exist. So now what I want to see, so if we think of this graph just very quickly, as I approach the given input 3, so as I'm plugging in some value here for 3, we'll call this 1, 2, 3, 4, 5. So as I'm coming at it from the left and I'm approaching this value here, I should be approaching this point on my graph because this is 3, negative 1. So as I move at it towards this side and I approach this input, my output is approaching this, the negative 1. Same thing, when I move at it from this direction and I come at that 3 as an input, I approach the negative 1 as an output. And we can do that pretty simply just with a couple tables. So we'll look at that. So I'll make a little table here, x, y, a second one. And now what I want to do is I want to come at this from the left side. So I'm approaching 3 from the left, so I'm going to come at that at 2.9, 2.99, 2.999. So I'm just coming at it from this position on the horizontal, coming at it from the left, so slightly below the value. And then when I come at it from the right, we'll start as 3.1, 3.01, 3.001. So I'm going to evaluate these. So as my x value is getting closer and closer and closer to 3, and this is getting closer and closer and closer to 3, my output value should be getting closer, closer, closer to the negative 1. And we'll use our calculator here to aid us in that. What I can do to kind of reduce some of the work here is I can put this into my y equals. We can take a quick look at the graph. We should know that this is linear. And so I see it certainly does appear to be continuous. And what we'll do is we'll go to our table set here. I'm going to go ahead and start it at, say, 2.99. I'm going to change this by tenths. Actually, excuse me, I'm going to change it by hundredths. And we'll go to our table. So you see when I'm at 2.9, this is at negative 0.8. When I'm at 2.99, it's at negative 0.98. And we'll go fill these other two here without changing anything in my calculator. When I'm at 3.01, I'm at negative 1.02. When I'm at 3.1, I'm at negative 1.2. Now I'll just change my graph here a little bit, or the table set. Change this there. We'll start at we see that value is negative 0.998. And I don't want to scroll through too many of these. We'll see it right here, negative 1.002. So again, what we're looking for here is that as the input, as the x value approaches 3, the value I was asked to verify that it's continuous at, my value for y is getting exceedingly closer and closer to this output, what I actually evaluated that point at. So that's coming at it from the left, and then this one coming at it from the right. As I get closer and closer to 3, the input value, my output gets closer and closer to negative 1. So yes, this is continuous at 3. Let's do the one right below it here. So we're going to set this up in exactly the same manner. So first step is to evaluate f of negative 2. So I substitute that in. So negative 2 squared minus 12 times negative 2, negative 12 times 4, and then minus a negative, so that's plus 24. So negative 24. So again, when I plug this in, I get this out. First step, the point does exist, so that's been checked. Now what we're going to do with our calculator here, pull that back up, is I'm going to plug this in. So negative 12x squared minus 12x. And we'll take a quick look at it. We know it's going to be a quadratic, and it certainly appears to be continuous. We know that's just going to extend towards negative infinity. And we're going to go ahead to our table here. Again, I'm going to make an xy, and as I approach it from the left, so negative 2, so that's going to be, let's see, negative 2.1, negative 2.01, negative 2.001. Then as I approach it from the right, so negative 1.9, negative 1.99, negative 1.999. And we'll go ahead and change this. I'm going to start at negative 2.1. Oops. 2.1. We'll go by. So at negative 2.1, I'm at 27.72. And at 0.01, I'm at negative 24.36. At negative 1.99, I'm at negative 23.64. And at negative 1.9, I'm at negative 20.52. We'll go change our table set here again real quick. Start there. And at negative 1.999, we're at negative 23.96. Go up here a little bit. At negative 2.001, I'm at negative 24.04. So again, what am I looking for? As my x value gets closer and closer to the negative 2, as I approach it from the left, and as I approach it from the right, my y value, the output, gets closer and closer to the negative 24. Indeed it does. So I verified that this is continuous at negative 2. And let's look at another example. So again, is this continuous at x equals 0? Well, this is a piecewise function, so I'm first going to verify that this point exists. I see right here that when x is 0, it is at 1. So yes, I verified that. I'll go ahead and make my graph. So as I approach it from the left, so as I approach 0, that's going to be like 0.1. Excuse me, from the left. So negative 0.1, negative 0.01, negative 0.001. And as I approach it from the right, okay. So let's see, anytime this says that x is less than 0, so for all these values, when it's less than 0, I'm going to be at 2 minus x. So I need to evaluate these. So I'll pull up the calculator again. So this is what I'm using. So 2 minus x. So 2 minus negative 0.1. So we'll see that's 2.1. And I can just say second entry. We'll change this to 0.01. That is 2.01. And one more time. So we can see it appears as I'm getting closer and closer, I'm actually approaching 2. And as I come at it from the right side, so that is values greater than, we see it is just simply x. So that's 0.1, 0.01, 0.001. So as I approach it from the left side, I'm actually approaching 2. So we'll see that when it's continuous, that x equals 1. When x is 0, it equals 1. So I'm actually approaching 2 here. And when I approach it from this side, it looks like I'm actually approaching 0. So this is actually discontinuous. And with this type of piecewise function, this one's approaching 2, this one's approaching 0. So this has a very specific value only at this given input. So this would be point discontinuity. So it's got a break there right at the exact value of x equals 0, and that is very specifically just the value 1. So that's point discontinuity. And then we'll look at this last example here. So we're going to evaluate and see, where is this discontinuous? Well, again, we know anytime I have this in the denominator, that when I get a 0, I will get an asymptote. And it will be discontinuous at those values. So let's go ahead and evaluate that. So what we're going to do is we're going to factor this. So I'm going to put the product of the first and last term in the top, and I'm going to put the middle term in the bottom. Now I'm looking for factors of -8 that will combine to make a 7. And I see that pairing is going to be right there, 8 and 1. 8 times 1 makes me an 8. 8 minus 1 will get me a 7. I know they need to multiply to get a -8, and when I combine them, I get a positive 7, so that's going to be the negative. And then what I do is I make a little box over here, and I'll put these terms in. Put the first term in this first box, last term in this box, and these are my middle two terms. Your algebra teacher may have shown you a different way to factor. This is how I do it with my Algebra 1 kids. It provides them some structure so they do it correctly. And then we just factor out from each one of these columns and then the rows. So 2x squared and 8x, I can pull out a 2x. -1x and a -4, I can pull out a -1. 2x squared and a -1x, I can pull out an x. And then 8x and a -4, I can pull out a 4. And again, if you just look real quickly, 2x and x is 2x squared, -1x and -1x, 2x times 4 is 8x. So we're kind of doing the reverse of how a lot of you were probably shown to double distribute, or instead of foiling, you used this operator in order to help you multiply these out. So we're just doing that in reverse. And then -1 times 4 equals -4. So these are my factors. Okay, so here's my factors, and we see this one is also presented in the top here, so those will actually cancel out. So really this all boils down to 22 over 2x minus 1. So when will this equal 0? Well, anytime 2x minus 1 equals 0, so I add a 1, divide by 2, so that's going to be when x equals 1/2. That will have a vertical asymptote. If I pull that up in my calculator here, I've already gone ahead and entered that in. Again, so I've got the original, which I can just input, no problem. And it's going to be the same thing as this. I'll make this, we will bold that one, so you'll see it's just going to lay right over it. So here's the original. You can just input that right in your calculator. And then once it's been simplified a little bit, we see it's the same thing, and we have this vertical asymptote. If I go to my table, I've got this error right here at 0.5, at 1/2. So this is discontinuous, and that would be that infinite discontinuity at x equals 0.5 or 1/2. So now let's talk a little bit about end behavior. And this doesn't have to be super complicated either. Really what we're trying to determine is, what does my graph do as I approach, infinity and negative infinity. So it describes what the y values do as the absolute value of x becomes greater and greater. So simply put, as you move to the left of your graph and to the right of your graph, what does your graph do? That's what we're trying to define. And so really you've got two things. It's either going to increase or decrease. There is a third. It could be a constant function, but most are going to be increasing or decreasing. And an increasing function is increasing on an interval, if and only if for every a and b contained in f of a is less than f of b whenever a is less than b. Really all this is saying, this is more of a technical term for it, but really all it's saying is as we read, and we read from left to right, so as I move over any given interval, moving from the left to the right, that my function is increasing or going up. That's all that says. And it's the same thing here for a decreasing function. As I read the graph, as I move from the left to the right, your graph is decreasing. It's heading downward. And the constant function is constant on interval if and only if for every a and b contained in the set, f of a equals f of b. And what that looks like is that is just a perfectly horizontal line. So just like you learned in Algebra 1, that constant function that's a horizontal line, simply y equals 3, that's a constant function. It's neither increasing nor decreasing, it's just considered constant. Again, always viewed from left to right, just like reading a book. So let's take a look. If I want to evaluate this, so describe the M behavior. So again, as I'm moving off to the left, so I can say, we'll say, as x approaches negative infinity, f of x, your function, approaches infinity. That's what's happening in my graph. As I move outward towards negative infinity on my x, I'm moving towards positive infinity on the function f of x. And as x approaches infinity, f of x approaches also positive infinity. So that describes the M behavior. Now, if I want to talk about the increasing and decreasing intervals, what I can say is just that the increasing intervals, so this is increasing. Remember now as we read left to right, I see it's increasing from here, and I'll just use notation here, set notation, negative 9.5, all the way over to, I'm sorry, that's the y value. From here, the x, negative 2.2, to here, 0.04. And I use the parentheses instead of a bracket like that, because if they're on this exact point, and that's what's indicated when you use this type of bracket as opposed to the parentheses, you're not either decreasing nor increasing, so I prefer to use the parentheses. I find it to be more accurate. And then it's also increasing, let's see, that's the only interval, because from here forward it's heading on towards positive infinity. So this would be the increasing interval. I'm walking uphill from here to here. Now the decreasing interval I see occurs right here. So I'm heading downhill. So that is also, so it's decreasing from the interval 0.04 down to 2.9. And that's all we really need to do. So again, as x approaches negative infinity, my function approaches positive infinity. So as I continue to move off here, this continues to head upwards. As I approach infinity for x, as I move off to the right, my function's approaching positive infinity. And then I have an increasing interval from here to here, and a decreasing interval from here to here. So that's what I've described. Take a look at one more. Okay, let's take a look at this problem. And we'll go ahead and pull this up and graph it in the calculator. So I have 2x squared minus 5x minus 4. And we'll go ahead and graph that. See, we get this quadratic. Go ahead and plot some of these values. And I have negative 1, 3. I have 0, negative 4. And I have 1, negative 7. have 3, -1. And I have 4, 8. So we'll just do something like that. So looks something like that. Again, I don't have any increasing or decreasing intervals because it's quadratic. So what we'll say is as x approaches -infinity, f of x approaches positive infinity. As x approaches, so as I move off to the left, I'm approaching positive infinity. So left going up, and as x approaches infinity, moving to the right, it's also approaching, my function approaches positive infinity. It's also heading uphill. That's all this says. As I move left, I go up. As I move right, I go up. So bring any questions with you tomorrow. We'll get a little more practice in class.